Okay, very well. So welcome everyone to our second Science Cafe of the autumn season. And this November, we will talk about light. The title of the presentation is Let There Be Coherent Light. For those of you who are new to Science Cafe, we begin with half an hour, 40 minutes of presentation by our speaker. And after, you will have the possibility, we have a question and answer session, and you will have the possibility of asking questions. And after that, our speaker will be staying with us. So if you want to just ask him personally something, in Finnish, for example, or in whatever language, then he will be staying here. And the speaker of this Science Cafe is Dr. Tom Kuusela from the University of Turku, the Department of Physics and Astronomy. Tom?
Yeah. Thank you. Is it working? Yeah. Okay, so just a little bit, few words about what I'm saying today. I start with short historical overview, some most important steps in the history of physics concerning the light, and after that I will tell some. I will show you some most important experiments in quantum optics. So.
And do you hear all?
Yeah. Do you hear?
Is that a bit noisy there?
Yeah. Okay, I can try to use this. Okay, so I start from the era of Newton, but there are also some other guys most important. James Maxwell, Albert Einstein, and Max Planck. So all of these four men has a great contribution when it's question about the concept and the essence of the light. So I will start with Newton. Of course, the history of light is much longer, but I start from Newton because he's the first one who has something really say about what is the light. Of course, people starting from ancient Greece, they have all kind of ideas and speculations. What is a light and how the eye will work and so on. But I will start with Newton. So at the time of Newton, some of these basic concept of geometrical optics were well known. For example, this reflection. So here we have a mirror, and people know very well that the input angle, the angle here measured against this normal of this surface is equal than the output angle also measured against this normal of the surface. So these angles are equal. This is a reflection. It was well known. Also this refraction, when we have an interface of two different materials, for example here we have air and water, people know that the beam of the light is bent in the water towards this normal, and of course there is also some portion of light is reflected from this interface. Actually, these basic laws, reflection and refraction, was known several hundred years ago in Islamic world, around 1000 or something like that. But this information was not transferred to Europe. There are many other things also in physics that they are first invented in Islamic world. But anyway, this was like a state of art at time of Newton. Quite important publication was made by Francesco Grimaldi. He was a monk and he studied waves, mostly water waves, but he also managed to show that with the light we can see this kind of phenomenon. It's diffraction. That means that when we have some plane wave here and we have a very small hole, after this hole these plane waves are not going in similar manner, but they produce like a cone after this very small hole. And he also realized that this is also true with the light. It was quite amazing observation because there was actually no scientific tool to make some beams like a laser beam like this one or or very small holes and so on. But he managed to observe this kind of dispersion, diffraction. And it was his opinion, and many other at the same time as Newton lived also think about it, that this must be evidence that light actually is a wave. Okay. Christian Huygens was another guy, another physicist on those years, and he called it wave theory. He believed that all these different geometrical optics phenomena can be explained by wave theory, and he also said that the colors. The common opinion was on those days that the white light is the original color of the light, the white. And when we see some different colors, red, blue, whatever, somehow this original white light is corrupted. And because it travels through the medium, for example, some glass objects, prism lenses, and so on. Newton argued that reflection and refraction can be explained only if the light consists of particles, some kind of particles. And he also thought that even this diffraction can be explained by terms of some kind of refraction. The argument on those days, the argument between these particle people and wave people was actually quite heavy, and Newton has very strong debate, especially with Robert Hooke, and the whole this discussion between these two groups was actually very dramatic to Newton. That after these debates, he refuses to publish anything, including his invention in celestial mechanics and classical mechanics in general. So Newton was silent for 20 years after this. And he hated this Robert Hooke, and there was other things also behind, but this was very dramatic time for Newton. And actually, it was Edmund Halley, tens of years later, came to Newton and asked to solve these movements or the movements of celestial bodies, and Newton said that yes, I have a solution for that. I have did it several years ago, but he refuses to publish anything because Edmund Halley was a partner with Robert Hooke, and it was very difficult to convince Newton that you must publish your results. So actually it was very close that we have no principle today. Who knows? And the reason was that argument between waves versus particles when question about light. Okay, but they are matter of geometrical optics. But Newton was the first one who really do experiments to show something physical properties of light. It's something totally different, physical. Then we are questioning about the essence of light. And he did actually huge set 44 different experiments, and he believed that after those experiments he can really prove that light consists of particles, but actually it is not true. But he was convinced by herself that he has proved that, but it's not. Actually, it was not true. But he made many experiments, and one of the most brilliant was extremely simple, but it was very clever. And he took a prism. Everybody, you know prism, and he guided some white light. It was sunlight, because there was no other such sources on those days. And after prism you can see the spectrum of colors, as usually. Then Newton took another prism and inverted it, and guided this spectrum of colors to this second prism, and then he can collect them together again, and he get out white light. So this sounds very simple, but this is brilliant idea. Nobody before him did this kind of experiment. And this proves that the white light is not the original color of the light, but the white light consists of different colors. So this is the first direct measurement of physical properties of light. Further, another experiment, again we have a white light prism, then we have a spectrum of colors there, and we just pick a small portion of the spectrum, the red part of the spectrum here, and put it in a prism, and we can see that nothing happens. So the red light is already red light, and you cannot anymore disperse it or to divide it in different colors. Okay, so that was a state of art at the time of Newton. Okay, he called these particles corpuscles, and he also, as this experiment displayed, he also showed that these corpuscles have certain color. So something physical properties can be seen by that. Okay, now then we must go further some 200 years, and then we look at what James Maxwell can say about light. I guess most of you are physicists, but maybe there are also other people, I guess so. So I will show during my presentation a few equations and solutions, but don't worry, it's not necessary to understand those. But anyway, I will show those because I also want to show how physics works. So we start with this great unified theory of electric and magnetic fields made by James Maxwell. And here are the equations. These equations, I can say these are iconic. There are 4 equations. Originally there was 20 different equations, but Maxwell, with the help of some other scientists, they managed to put them to 4 equations. These are iconic. These are as important as Newton's laws for mechanics. I can say that maybe even more important. There, you can see there's electric field, and there's a magnetic field from charges, current, and so on. So these are equations which describe actually every phenomena where you have some electric field, magnetic field, current, charges, whatever. So it's a huge general theory, covers multitude different kind of situations. If we have such a situation that there are no materials, no charges, just a vacuum, nothing else, just a vacuum, then we can derive from, a little bit backward. We can derive from these equations an equation just for the electric field. So this is very simple, at least all physicists here can immediately solve these equations. This is very simple equation, and it has different kind of solutions, but the most simple one is a traveling wave solution, like this. Yeah. So here is this electrical field in x direction, and this wave travels to the transverse direction, to the z direction. But for non-physicists, it's not so important. But what is important here is that here we have a free parameter. It's a wavelength, and here we have a speed of this traveling wave. So if we look at the picture, the electromagnetic field is going to this direction, and this blue one here is an electric field which oscillates in the plane, and in this case, this light is linearly polarized. I will return this at the end of my presentation. But anyway, the wavelength here is, you can see this from a minimum or maximum to the next maximum. This is a wavelength. It's a free parameter. And here we have some amplitude. It just tells how large is this oscillation in electrical field. And the velocity is here. This mu0, epsilon 0, they are material parameters or constant, or in this case they are vacuum values of those parameters. They are magnetic permeability and electric permittivity, permittivity. They are constants, material constants, vacuum constants, which you can determine independently with some other kind of experiments. But they are like a natural constants. That's important in the next step. Okay, so we have now this kind of solution. Is it a question of light or not? We don't know yet. Let's look at a little bit more closely this solution. When you put the numerical values of mu and epsilon to this form here, you realize that it has a value equal to the velocity of light. The velocity of light was measured first time 100 or more than 100 years before Maxwell's invention. Maxwell by himself, he first thinks that this is just by accident. Okay, it seems to be that it is approximately same as the velocity of light, but he believed that it's just by an accident. But then quite soon some experimentalist, Hertz was one of those first ones, made experiments with the radio waves and later with the light waves. It turns out that this traveling wave solution of Maxwell equations in a vacuum actually also is a model of light. And the wavelength, the free parameter here in a solution is actually the color of the light. So now we have a real physical and also mathematical explanation of why we have a different color for the light. Okay. So as a conclusion, light is electromagnetic wave and it travels with the speed of light. We use the symbol C for that. And also the color of the light, it depends on the wavelength of this magnetic field. There seems to be some kind of contradiction because Newton thought that light consists of particles. Now Maxwell says that it is a wave. So maybe there is some contradiction or not. But I will also return this a little bit later. Next, we need Albert Einstein to give her contribution to the theory of light. And we must start again with Newton and this classical mechanics. In classical mechanics, we have so-called Galilean rule for adding velocities. Here is father. He's pulling his daughter with the velocity of 1.5 millimeter per second, and the daughter he throw the snowball with he's pulling with a velocity of 1.0 meter per second, and the daughter he's throwing this snowball with a velocity of 1.5. And this classical mechanics made by Newton says that the velocity of the snowball from point of view of this observer here is 2.5. So we just add the velocities together. And it works very well in almost all cases. Okay, so what about the light? If you remember 2 slides before, the velocity of light depends only these constants mu0 and epsilon 0. And there is no contribution of the velocity of the observer. It seems to be a constant. So the people was a little bit confusing that what does it mean actually. And then they invented hypothetical media, so-called ether, which carries electromagnetic waves. This ether was very peculiar material or substance or media, whatever. It's believed that electromagnetic wave cannot be propagated in real vacuum. It needed some substance. In a similar manner than we have these sound waves. In a vacuum, we cannot hear any sound waves. We need some gas, let's say air, and it has certain velocity in the air. And if we put sound waves to the, like, let's say, a solid metal bar, the velocity is much higher. In the case of light, the velocity is extremely high. It was known those days it is extremely high. That means that the elasticity of the medium carrying electromagnetic waves must be very, very low. It must be very stiff material. But at the same time, it's totally transparent, and normal bodies can propagate through this media without any difficulties. So it has a very contradictory features, this ether. But it was commonly believed that really this kind of ether is needed to explain the propagation of the electromagnetic waves. And also because it seems to be, if you look at the solution, that the velocity is constant. So maybe it is constant in this very special frame, this ether frame. So if we believe that this Newtonian mechanics is valid and we are moving related to this ether, then the velocity of the light should be different to us. Okay? And how to do experiment? Because the velocity of light is very high, so to test that is this Newtonian or this Galilean adding rule true or not, you must also have some observer moving quite fast. 1 or 10 meters per second is not enough. It must be at least a small fraction of speed of light. And such an experiment is very difficult to do in laboratory. But let's put our laboratory fixed on Earth. And we know that Earth is moving very fast. At least it circulates the sun, and the velocity is very high. It was known already those days. And when we look at the speed of light on the surface of Earth in different directions, and Earth is moving through this ether, we should see some differences in the velocity of the light. And actually these kind of experiments were performed by Michaels and Morley in 1887. They use very accurate interferometers, similar kind of tool which has been used recently to detect gravitational waves. Actually, it was exactly the same kind of device, of course, much smaller, but similar type. And they did not observe any changes in the speed of light. So Einstein concluded that first, it is not either type of medium or substance does not exist. We don't need it. And the second one is that the velocity of light is constant. This is actually one of the axioms of special relativity. Special relativity has only two axioms. First is very general one, which says that all physical laws have an equal form in every coordinate systems which are moving with constant speed. And the second one is that the speed of light has the same value in every coordinate system, and nothing else is needed. And then you can derive all these results of special relativity. So actually the speed of light and light is essential part of the special relativity. Okay, then a couple of other equations. Starting from these two axioms, it takes a couple of lines. We can derive two relationships. The first one, almost I guess that for non-physicists, you almost know this first relation or equation here. This is a total energy of relative particle. And in the case that, okay, m is a mass, c is a velocity of light, p is a momentum of the body. Momentum in classical mechanics is same as mass times velocity. That's a momentum. And then we have velocity of light here. So if the body is in rest, it's moving at all, then we can omit this last term here. And then we have a square root. We can remove this outer power 2 here. Then we have very common result. E is mc power to 2. Everybody knows that. Even if you don't know anything about physics, you know that E is m times c power 2. So this is a little bit more general version of that. This one is like a rest energy, and the last one is like a kinetic energy in relative form. The second one is not so obvious, but if we have this relation that the momentum is mass times velocity of the body. This is an equal form in special relativity. But it is a little bit more complicated because the masses can change and there are other effects in special relativity. Okay, but if you believe that these are valid one, let's take a hypothesis that we have a particle which has no mass at all. Okay, put it here, mass is 0. So then we can omit this term here. We have only this one. Once again, we take a square root. We have E is equal to P times C. And then we put it here. We get P times C divided by P times C. We get the 1 here, which means that V is equal C. So the special relativity not actually predict, but it allows that it is possible that there are such bodies or particles which has 0 mass, but if they have 0 mass, then they must move with the velocity of light. I think this is quite nice result. Okay, and Newton and some other guys call those particles photons. So now we have some kind of particles. And maybe this particle wave contradiction is somewhere here. Who knows? But still something is missing. Maybe we can say that the special relativity predicts the existence of photons, but the special relativity cannot say anything about the energy or the momentum of those still hypothetical particles. So something else is needed, and then we must call Max Planck. There was also some other difficulties. On those days, there are a lot of experimental measurements on spectrum of various sources, and one of the most common sources was so-called Blackbody. Blackbody, actually, is a cooking plate, hot cooking plate can model quite well Blackbody. Blackbody is basically it is a material which has no characteristic output spectrum. It can be like a carbon ball or plate or something like that. But anyway, the cooking plate, everybody has seen that when the cooking plate is hot enough, you can see red light. And it means that the temperature is about 600 degrees. So it's quite close to Blackbody. The Blackbody radiation spectrum was measured very accurately, and it's like this. And there's only one parameter which affects on the shape of this output spectrum. Here we have some, I don't know if you can see, but there are some several thousand of degrees here. Let's say here is 6,000 degrees. This corresponds to the temperature of the surface of the sun. It's about 6,000. And it's like a continuum, and here is a visible range here. These curves were measured very accurately, but there was no theoretical explanation why the Blackbody radiation has this kind of output spectrum. So also Planck was thinking about it. Actually, he made several trials. Normally in a textbook, just say that Planck made a couple of assumptions and solved the problem, but actually he used a lot of work, several years, all kind of trials and errors, and finally he made two essential assumptions. First is that these photons can be regarded as I can say that they are in a thermal equilibrium. He used some, actually he misused some principles of thermodynamics or to the photons. Normally there are some real particles, but Planck used these thermodynamic principles and applied them to the photons. That's the first assumption. And the second one is that this energy is absorbed or emitted only in quantized form. So it is not continuous, but it's somehow quantized form. Planck believed that that when he has completed all his calculations, he can put this quanta to the limit of zero. But from point of view of Planck, unfortunately, he couldn't do that. Thanks to us, that it was not possible, because otherwise we have no quantum physics, and this was the first time that we have something totally new in physics. This was a starting point of quantum physics. Of course, it takes much more, some 20 years more work, but this was the very, very first moment that somebody realized that the true nature has something very peculiar features, some very peculiar properties. And this was the first one. Unfortunately, I cannot go to the details of this calculation. It's not very complicated, but it's not possible. Okay, and we can just pick one result from Planck's work. That means that the energy of these photons is, if you take this form first here, is inversely depending on the lambda, which was the wavelength, the color of the photon, or the frequency. These are just same thing, but different parameters or quantity here. We have either frequency or this wavelength. And then he introduced this very, very important, most fundamental physical constant, Planck's constant, this H here. Yeah. So this is energy of the photon with because the special relativity cannot give us that number. Okay, so now we have quite complete picture. We started from Newton through Maxwell, electromagnetic wave. Then we need something from special relativity and small portion from Max Planck. But do photons really exist? And on those days, Planck's days and Newton, there was made some experiments with light and maybe I can explain first what kind of experimental setup we have. This is a vacuum tube here, and here we have a cathode and anode, and then we illuminate this cathode with typically monochromatic light, let's say red light or green light or blue light. And people have measured in this kind of setup that with certain light you can eject electrons from this cathode here. It depends on the material, what kind of color you are. It's really needed, but at least with some kind of color you can eject electrons from this cathode, and then they are going to this positive anode, and you can measure the current here. But sometimes you cannot eject electrons, sometimes you can do it. This experiment was well known, but nobody can explain what really happens here. And let's say that we have a potassium target in this cathode here, and if we use a red light, we cannot eject any electrons. And it's no matter how many red photons we put on the surface, we cannot take out the electrons for this potassium material. But if we put green light, we can take photons out of this surface, and then it depends on the intensity of the light. And if we have a purple or red, purple or blue or whatever, we can also eject electrons from this material. If we have this green light, we can eject electrons, and then we can measure. Actually, if we do these kind of experiments with several different monochromatic light, here is a frequency, but it's basically the same as a wavelength. We can see that the maximum kinetic energy of protoelectrons. With this setup, we can measure what is the kinetic energy. Actually, what is the speed of the electrons when they escape from this cathode material here. We can measure the kinetic energy. And here is some minimum frequency when we can eject eject electrons, but if the frequency is a little bit lower, we cannot eject any photons. And the extra, let's say in case of potassium target, we need at least minimum 2 electron volts to eject electrons. And if we have photons with energies less than these 2 electron volts, let's say for red light, you can see this is a little bit lower. We cannot eject all. Here we have a little bit extra, 0.25, and here we have more extra. So we get this kind of result here, and here we can say that if the frequency is exactly this one, we can just eject the electrons, but they get no extra energy to move from the cathode. This kind of result was well known, and Einstein knew this Planck's new results and this quantized form of the energy of the photons, and actually with this kind of very simple equations, Einstein got his Nobel Prize. The paper is extremely short. If you look at the original paper, it's extremely short. But basically with this one equation, I will not go to any more details, but it just explains this kind of situation. Okay, but we can believe that yes, this is, now we have proved that photons exist. Actually, it's not true. In most textbooks, photoelectric effect is introduced as that it can prove that photons exist, but actually it is not true. Because we can think that it is merely the property of the material, not the photons. But that's a detail. Okay, now let's look at a little bit different type of light. The blackbody radiation, it is something like this. There are all kind of wavelengths. Typically, the spectrum is continuous. If we have monochromatic light, basically we have only one color photons there, or at least the wavelength range is very, very narrow. Maybe not just exactly one wavelength, but the wavelength range is very, very narrow. But the phases are different, because now it's just an electromagnetic wave. Think about it as an electromagnetic wave. The phases are different, so that means that the minimums and maximums do not coincide with each other in this light beam. And then we can have laser light or coherent light. In that case, it is monochromatic, but also the phases of the different part of the beam coincide. So we have minimums and maximums exactly in the same position. This is just a trivial model of laser light, but it is something like that. In most cases, this is enough if we want to look at it. If we take, let's say, laser light, this one, I mean my pointer, this is a laser light. So if we take this kind of laser light and use some neutral filters so that we decrease the intensity more and more and more. And then we look at, let's say that we have a perfect detector which can measure very, very dim light. If we have a dimmer and dimmer laser light, then we can see that it is not anymore even, the flow of the photons or whatever it is. It is somehow noisy. It consists of some kinds of, how can I say, quantas or corpuscles or whatever. It is anymore, it's not continuous. Actually, even if we have a laser light like my pointer, and if I look at the intensity of this light very, very carefully, I can see that there are some constant background, and then there are small oscillation above or like above this very high constant value. There are some small noise. People working with the lasers call this laser shot noise. It is also well known. But it is easier to look at this noise when the intensity of the light is very, very low. And then it looks like this one, that there are photons arriving. And in the case of laser light, these photons arrival times are totally random. They are totally random here. If we have a so-called single photolight, I will return this at the end of my presentation, then it can look like that photons are coming in random fashion, but the difference comparing to this very dim laser light is that we know exactly when the photons are coming. So we know the arrival times. But they can be random, but we know when they are coming. That's a big difference. So here is a simulation. Let's say that we have a landscape, then we have a camera, some digital camera. It is ideal, perfect digital camera. That means that the quantum efficiency of each pixel is 100%. That means that if some photon is hitting one pixel, we can detect with the probability of 100. And let's say that there are no thermal noise. Basically, we must cool the pixel to 0 Kelvin temperature. And also there are no electrical noise. We have a perfect camera. And we take a picture of some landscape. And here is average number of photons per pixel. First, it's very, very dim light. Now here maybe you cannot see anything. Maybe not here in this screen you cannot see. Maybe you can see something here. It's like a very noisy. Some bright spots there and there. If we increase the intensity of the light, gradually we can see some figures here, but you can see it is noisy. And if we increase the intensity, finally we have a nice picture. Unfortunately, this is not yet possible, except in very, very special cases using extremely expensive cameras. We can do this kind of experiment that we gradually increase the intensity, and first we see just the noise, and then we have a quite noisy picture, and then gradually when we increase the intensity, we get a very nice picture. Actually, nowadays the best cameras works quite close to this shot noise level. Even the cameras in the mobile phones, they work quite close to this shot noise level. That means that it's no way to anymore increase the sensitivity of the camera, because there are this ultimate internal or inherent photon noise. We cannot go any further. It's no way to increase the sensitivity anymore. Of course, we can increase quantum efficiency, but the picture actually is noisy, so we cannot go beyond that. It's a real physical limit, which we cannot go over that. Okay, now a little bit more about coherent laser light. As I said before, the arrival times of the photon is totally random. If we divide this light to equal time slices, like that, some slices there, and then we count how many photons are in each of these slices here. Let's say that's N1, N2, and N3, and so on. And then we calculate how often in our time slices there are no photons, how often there are 2 photons, how often there are 3 photons, and so on. So we create like a distribution, how many photons there are, or what is the probability that in a time slice has certain number of photons. And then we get this kind of results. Quite few cases that there are no photons at all, and in this case maybe 5 photons is the most probable case that in our time slice had 5 photons and so on. This is also very fundamental distribution. It's called Poisson distribution. It is common to all random processes where the quantity is like a number. Here is a number of photons, but it can be some other kind of process. But the quantity is like a number. Then we get the Poisson process. Somehow it's quite amazing that normally I can say that most of the physicists also believe that the laser light is the most, how can I say, well-determined source of light, but actually it's totally random from point of view of quantum physics and quantum optics. So it's basically totally random, but it behaves very well. But that's the way. If we have a thermal light, this distribution is totally different. But I have no time to go that. But the thermal light is totally different. This is, I can say, at least indirect evidence that photons really exist. From in quantum optics theory, we can easily predict this result, but it's quite difficult to measure, and actually it has been possible only, let's say, 30 years. Because we need a detector which has a quantum efficiency high enough. Before, let's say, experiments older than 30 years, the best photon detector was so-called photon multiplier tube, PMT. But the PMT has a quite low photon efficiency. Typically, it's only procents. It depends on the wavelength, but typically it's only a few procents, and that means that it takes random sample of the light. And because you take a random sample of light, no matter what is the structure of the light, because you take the random sample of your light, you always get Poisson distribution. So you need a detector where the quantum efficiency is some 60 or 70 at minimum. Then you can really construct this Poisson distribution. So it's basically quite new that you can really measure it. Okay, then maybe we believe that photons really exist. Then look at beam splitter. Beam splitter is very, very basic optical elements in quantum optics and of course in traditional optics. Basically it's like a plate of glass, and you put on one surface a very thin layer of metal. And it acts like this, that let's say the intensity in what you guide to this beam splitter is 100%. Half of that is transmitted and half of that is reflected. That's the name. That's the reason that the name for beam splitter. It splits in two different parts. Now 50-50. If you look at the quantum picture of beam splitter, and let's say that we have a singular photon source. So we put a singular photon here inside this beam splitter. Photon is something that we cannot divide anymore. We cannot divide photon anymore. So it goes either here or it goes either there. But you cannot split it. Then we have a singular photon. And this is totally random. We cannot say when we put one photon here, is it going here or here? It's totally random. And that means that it is not random just because we don't know. Quantum mechanics tell that it is totally random, but quantum mechanics tell what is the probability to get photon here. Quantum mechanics or quantum optics tells that it is 50% and it's 50% here. But actually when we put one photon there, there's no way to know is it reflected or is it transmitted. And this is a strong evidence about the non-determinism of quantum world. It's very simple experiments, but it really says that this is normally we have many kind of physical processes which look like random, but in most cases they are just highly complex systems. There are many freedoms and particles and so on, and it looks like that it's random, but in most cases it is not actually. It's not truly random. Or maybe it's a low-dimensional system and it is chaotic, but it looks like random. But this is something really random process. This is a quantum mechanical non-determinism. Okay. Little bit more complicated experiment. So here we know that the photon must go here or here. We don't know yet, but we can just tell what is the probability. Let's put two photons simultaneously to this beam splitter. So this photon can go through or it can be reflected. This photon can go through or reflected. Now these photons are identical. It's most important that the photons are totally identical. The identical means that they have same wavelength, color, and the polarization state is same, and they are coming simultaneously to the same small spot of space at the same time. That means that they are identical and they are coming simultaneously. So what we can expect to be the outcome of this kind of experiment? This is, of course, one possibility. Seems to be that maybe this photon goes there and this there, or also it's possible that this goes there and this there. So we have one photon here, one photon here. Actually, there are the two cases, but we cannot separate the two cases because the photons are identical. We cannot put any label to photons. So we cannot say which one goes which direction, but anyway, this seems to be one possibility. Or both photons are going there, or both photons are going there. But what happens when we do these experiments? We can do this in a lab. I can say that this is not easy to do, but we can do this in lab. And what happens? This case never happens. And quantum mechanics can predict that for some reason. If you look at just one photon in a beam splitter, and now we have two photons in beam splitter, we can see that something different is happening. And the reason is that the quantum mechanical system must be always analyzed as a whole. The quantum mechanics is a holistic theory. So in this case, we cannot analyze this two-photon case in beam splitter from the results of one photon in a beam splitter. This is a very, very important aspect in quantum mechanics. We must always solve or analyze the system as it is. It's not possible to reduce to the smaller part. In some cases, yes, but in most cases, it's not possible. We can take the whole system and solve the whole system, and then we can predict this kind of result. This is very famous experiment, HongouMandel experiment, and this experiment or setup has been routinely used in quantum optics just to show or just to check if two photons really are identical. So this is a very, very, very important routine check for that. Something about interference. Sorry. Yeah, if they are not identical, let's say that the wavelengths are different, polarization states are different, then we have all these different cases, these three different. But only when they are identical, then those possibilities are excluded. Yeah, thank you. That's very good point. Okay, interference. Everybody has seen it somewhere, but let's look at what is question about in interference of waves. So here we have two waves, wave 1, wave 2, and when they coincident, that means that the minimums and maximums are exactly in the same positions, then the sum wave is larger wave like here. But if they are, now they are in phase, but if they are totally out of phase, then we get the zero result. This is like the interference. And everybody knows this. If you look at, let's say that you take a pool of water and with your finger you do like that, you can produce circular waves there. And if you take two fingers and do like that, you can produce two sets of circular waves, and in the middle they interact, and you can see these kind of patterns there. Everybody knows that. So we can have a constructive or destructive, and if the phase is something between these, we have different possibilities there. More or less, we have between these, we have in some point they can strengthen each other, or some point they can weaken each other. Okay, so we can do this interference experiment also with classical electromagnetic waves. With light, unfortunately, it's very difficult to perform this experiment when we have two separate sources of light. It is possible. I have seen one paper of that. Actually, one paper of that, but it's very, very difficult. Let's say that you have two very high-quality laser sources and you try to put them to interference. It's very, very difficult to do. It is possible. Basically, it should be possible, and I have seen one paper of that, but it's extremely difficult to do that. So the easier way is that we have just one source here, and we split it with beam splitter in two parts. That's much, much easier. Because then the wavelengths are automatically the same, and we must only take care of the phases of these two parts here. So the wavelength automatically, of course, because the one source is just to divide, the wavelength is equal in both parts. And then we have a mirrors there. They just reflect those parts here. And once again, the interference is easier to perform in a beam splitter again, and depending on the phases when they interact here, we get they can be in phase or out phase or something between of those. And if we have a screen there, and also if we tilt a little bit with our interferometers, that these angles are not exactly 90 degrees, we can get very typical interference patterns here. This means that here when we have a bright stripe, then they are in phase, those two waves. And when we have a dark stripe in between those bright ones, then they are totally out of phase. Then we have a dark stripe there. And the phase condition we can change by moving a mirror a little bit. We can trim the interferometer quite easily. Of course, the movements must be very small, because let's say if we are doing this with the visible light, then the wavelength is some 400 or 600 nanometers. We can move the mirror only few tens or maybe a couple of hundred of nanometers, and then we can see immediately differences in these interference patterns there. This is also routine measurement in a lab. Okay, but let's take single photon as an input light source here. Okay, we know that the photon can go there, it can go there. Again, when the photon comes here, it can go there, it can go there. Or is it going here, it can go there or there. If we put, let's say, 1 photon per second to this kind of interferometer, what we can see? And let's say that we have some kind of perfect detector here as a screen, that we can really say when the photon hit and where the photon hit the screen. So when we have a few photons input to this system, this interferometer, we get this kind of picture. They seem to be totally random there. We put more photons, no, almost random, but maybe we can see some structure there. And if we go more and more, we gradually see that the photons, it's more probably that the photons comes to these kind of stripes here. And if we have a huge amount of photons, we run this experiment again and again and again, let's say 1 million times, we get this kind of distribution. And this is exactly the same as with waves. But you must remember that it consists of these individual cases here, that these are not totally random, but anyway we cannot we have like a spot here, and only when we have many times done this same experiment, gradually we can see the similar kind of distribution as we have with waves. Further, if we cut this part here, so the photon cannot go this direction at all. So only photons which are going here have a contribution on this distribution. In that case, we have no interference patterns at all. We just get the photons in one little bit wider stripe there. That means that if we just go back to this basic experiment with the beam splitter, we knew that it must be go here or must be go here, but now if we cut this part here, we get no interference. That means that after the beam splitter, the photon must somehow go to both, using both parts. So somehow it goes here and it goes here. So in quantum mechanics or quantum optics, we say that after the first beam splitter, the photon is in a superposition state which somehow includes both parts. So is it a particle or not? It's interpretation, depends on your interpretation, but somehow it uses, of course these are metaphors and you don't take these too seriously, they are just metaphors. In quantum physics you must be very careful what kind of words you are using, because normally when you try to explain these kind of phenomena and you use words which are extracted from the macroscopic world, you somehow explain it wrongly, or you give at least somehow incorrect impression what is going on there. So the quantum world is something different. Okay. this was the basic beam splitter, 2 photons in beam splitter, and this interferometer. These are the 3 basic experiments where we can explore the most fundamental aspect of quantum physics. And finally, how to create singular photons. We cannot use very dim laser light because normally we must know when the photons are coming. So we must produce singular photons using some different kind of system or apparatus. This is a schematic picture. We start with the pump field, normally the laser light. Then we have some suitable material in original state. Then we excite it. It basically means that the energy of the system, is it a molecule or some ions or atoms, they go momentarily a little bit higher state of energy. But it relaxed very soon, let's say in fraction of picoseconds or femtoseconds, and we go back to the original state. But at the same time, it's possible that we create photon pairs. This is extremely rare process. Let's say that we have, I don't know how many photons here, but let's say we have 10 to some 25 photons per second. 10 to power 25, extremely many photons. Then we can get these pairs maybe a couple of hundreds per second. So it's extremely low probability, but it's not zero. Very, very low probability that we can create 2 photons. This is very, very rare process. And sometimes we can even produce 2 pairs or even 3 pairs, but they are even more unlikely. How we can, what is actually, this is like a virtual state, and virtual state is just a fancy way to physicists to say that don't ask any details. You can put everything there. Yeah, even some very nice textbook of quantum optics in the page 3 you can find that there's a virtual state, but then you don't talk about it. No, okay, you can do it, but it's a very nice way to say that don't ask any details. I really don't know what are virtual state, but this is just like a scheme. Yeah. But how we can do it actually in a laboratory? First, we need special material. It is like a crystal material. It's a transparent, and it must be birefringent. Birefringent means that no, this is quite technical to non-physicists, but it means that the refraction coefficient is different for different state of polarization of the light. And it must be non-linear. Non-linear means, okay, linear material is, let's say, like a piece of glass. No, it's linear. That means that if I put red light into the glass, I get the same red light out from this piece of glass. Non-linear material is it's such that if I put red light in, I can get something other colors out. Then it's non-linear. That's a minimum. At least we need that kind of material. There are some special materials used in these single photon sources, like beta barium borate and what is okay, that's the most common, and some lithium niobate and something else. There are there are only few different materials which are using this. They must be highly nonlinear. They must be transparent, birefringent, and suitable crystal structure and optical properties and so on. I will not go to the details. But anyway, we have a laser beam here, and then we can produce the photons, but the photons are coming out from this kind of light cones. The opening angle is typically a couple of degrees. It's like a light cone. And it's totally random fashion where we can get the photons out. But let's say if we have a photon out here, then the other photon is in the opposite side of this pump beam. It comes here. If we get the photon here, the other one is coming here. So this is a way that we produce photon pairs. And we can put a detector here, and when the detector says click, it has detected a photon, then we know that the other photon is here, and we can guide it, let's say, to the optical fiber and put it in some experiment, let's say interferometer or beam splitter. So that is a way that we we can produce single photons in a controlled fashion. We know when they are going out. So this, in this sense, it is totally different than a dim laser light. Here is an actual picture of this. I have this. There's another. Okay, maybe I explain the other type of first. This is another type. There are type 1 and type 2. Here we have two cones, light cones. And they are in such a way different that the polarization of the photons is different. Here they are vertical and here they are horizontally polarized. That means that in a classical picture we have a vertical plane where this electric field is oscillating and other is horizontal. And I have in my lab, I have both of these kind of sources. And here's actually a picture of this light cone. It's difficult to take this picture because the light is extremely dim and you must somehow to suppress the bump beam which has 10 to let's say 20 times higher intensity, so you must somehow to suppress it. But here is a light cone and here is another one. This one, the intersect here. And in this case, we can produce this kind of state. Once again, those non-physicists, don't be afraid. This is just a handy way to say that photon 1 is horizontally polarized and photon 2 is horizontally polarized. Nothing else. It's just a symbol, like a shortcut to say that it's nothing else in this equations or statement here. And here, if we pick photon here and photon here, we get a similar type of so-called product state. Now we have vertical polarized photon here and horizontally there. It's like this. But okay, but if you can see that these two light cones, they can intersect. Here they are intersection. So if we pick the photons from those intersections, and in a quantum physics, they are like a thumb rule. It is not a real rule, but it's like a thumb rule that if we put our detector here, we don't know is the photon coming from this light cone or that. And in quantum physics, it's like a thumb rule that if there are several possibilities, several choices, and I don't know which one I should select, I must take both one. So I can take both one. That means that in this case, if we pick the photon from these intersections, our two-photon quantum state is like this. That means simply that the photon 1 is at half, it is a horizontally polarized, and one half it's a vertical polarized. The polarization is, you can say that it is not well determined. It has both properties simultaneously. This is just once again a metaphor. I don't take it so seriously, but you can imagine that it's not well determined. Somehow it is partially horizontally, partially vertically. It's not well determined. And this kind of state was quite interesting, and this is my final. I hope that I have not used too much time. Let's take, this is so-called entangled state. It's very special. It's just one example of superposition principle. In our interferometers, we have also superposition, the superposition of two parts. Now we have a superposition of polarized state. And if we make measurements with these two photons, and let's say that we have two experimentalists, experimentalist A and experimentalist B. A measures the polarization state of the photon 1, and the B accordingly the polarization state of the photon 2, and they make some measurements. Let's say here there are 7 measurements here, and we can get H or V. We cannot say which one we get out, but we know according to quantum mechanics that the probability to get to H is 50% and probability to get to V is also 50%. And the experimentalist B do exactly the same measurement, and he also get, when these states are produced many and we have done many measurements, he also get half V, half V, half H, half V. Okay, I can think it's quite easy to understand that because this is totally symmetric here, that we can get H or V, and this is totally symmetric here. Don't worry about this factor here, it's not important. But what is remarkable, when we compare these two lists of measurement outcomes, we can see that they are complete autocorrelation. So when experiment A gets H, the B gets V, and vice versa here. So somehow, let's say that the A makes those measurements first, and then the B do his own measurements. So somehow the outcome of the B depends on the result of the A. But we must here understand that these photons can be very, very far away each other. We can put them, let's say, to the optical fibers, or we can go to the outer space and let those photons to travel, let's say, tens of thousands of kilometers, and A do the measurements, B do the measurements. There are no way that they can somehow to change information or energy or whatever, and still they can see that they are total anticorrelation. Every time A gets V, the B gets H. It's no matter what is the order of these measurements, but always there is this kind of anticorrelation. And this is just the manifestation that the quantum world is non-local. We can get some correlations which do not depend on the distance or order, something totally different kind of correlation than we are familiar with the classical picture of nature. Okay. I just found from internet quite nice description of light. I really don't know the writer. It was maybe some company who's selling diamonds, and there was this kind of text and another one. But I was quite nicely said what is question about in photons. First, the upper one is like a quantum picture, and lower is from point of view of special relativity. Thank you.
Okay, Tom, I did it, yes, it has happened. Never mind, something will be careful there with your feet. Thank you so much, this was a super interesting talk, and I'm sure that there will be a lot of questions. I have to say that Tom actually is an experimentalist in the quantum optics laboratory of the University of Turku in the Department of Physics, so he really has experiments, as he was saying, in his lab, where he can see these things, entangled photons and everything he was talking about, more or less, I guess. So with this particular mention that I wanted to make at this point, I am ready to ask if you have questions at this point. Yes.
This is kind of a funny question, I suppose. I was thinking a few years ago about light, and then I had this crazy idea that what about if the basic principle that the light travels in waves, if it's not true, if it travels in spirals?
Spirals? Yeah. Yeah, no, actually, yes. And in fact, even the photons, they have several kind of I can say characteristics. One is its polarization. It can be linearly polarized, but it's also possible that the polarization, if you look at the classical picture, means that the direction where the electric field is oscillating. But the polarization can also do like this. So it's like a spiral. It's also possible that the wave front of the light, it also is like a spiral or double spiral or even in a multitude like a spiral. So I don't know, is it related your question to that, but these are so normally we say that this polarization is like a spin orbit. If you look at think about the analog from some celestial bodies, let's say Earth and Sun. So the angular angular, like you say, angular movement is that the Earth is circulating sun, but at the same time Earth is also spin around this axle. So the photons, they are also similar kind of properties that they actually not spin, but we call it spin because it's a very similar kind of quantity than the classical spinning around the axis. And then it has also this angular type of movement, but it's, of course it's not analog. And this angular type is multidimensional. In the polarization, we have two possibilities: horizontal, vertical, or left or right-handed. But this angular moment or angular movement, there is infinite number of different, like I said, modes. And nowadays it's very, very active research on this topic, because then you can code more information to single photon. Actually, you can put infinite number of bits. That means infinite amount of information in one photon. In principle, of course, there are a lot of technical difficulties, but because if we, as you all know, more and more information must be guided through the optical fibers. So if we can use this angular type of freedom, we can put much more information to single photons and increase the throughput of the data networks. Yeah.
Okay, thank you. So, more questions? Okay, maybe I do have one. You were mentioning some of the properties of light, especially in the end, that are more perhaps surprising, like entanglement or quantum superpositions. Can you tell us why you think that this might be, if they might be useful, for our society, or is it just fundamental science?
Yeah, this entanglement is just a starting point. That with entanglement you can do all kind of fancy things. That can say that this quantum cryptography and quantum computing, they are more or less originating from the possibility that quantum system can be in a superposition state. Is it light or atoms or molecules? So there are many applications for that. Even real, I can say, commercial application that it use this entanglement as a part of the system, where you can let's say that you can produce information channels which it's not possible to hear without telling to the receiver that somebody has hear this information channel, that you cannot hook it without telling this receiver that you have hearing the information channels, and this quantum computing is based on this phenomena and the others. Yeah.
Related to that, I didn't know actually. You were mentioning that the existing cameras, even the cameras of mobile phones, are already working at short noise limit.
Yeah, they are very close to this short noise level already. Yeah. So normally these professional cameras, they are cooling down to decrease the thermal noise, but the electrical noise is already so low, and when you cool it, let's say some 30 or 50 degrees below zero, the thermal noise is very low. So then the only source of noise is actually photon noise. So we have already reached it. In professional cameras, it's a daily routine to tangle with that noise level, and with mobile phones we are maybe a little bit higher, but there is no way actually to go lower noise level anymore.
So we don't expect any. We don't expect any improvements from this perspective.
No,
okay,
no.
so we don't buy new cameras.
No. Of course, you can increase the quantum efficiency in different wavelengths. Okay, there is lot to do.
But in the cameras, I mean, like quantum efficiency for the camera.
but it's very high already. Actually, it's very high already at some 60 or 70%.
Oh, besides, we wouldn't probably even be able to see the difference at this point.
That's true. Yeah, it's quite amazing that how far away those cameras are nowadays. That they are really in this physical limit.
Yes?
Yeah, so I was wondering about this wave splitter that you showed and these interference patterns. Did I understand correctly that it's important that you have only single photons and also that you know the timing of the photons, so you know when they're coming in?
Yeah.
How can that be? How does it influence this interference spectrum?
No, actually, it's not,
if you just randomly shoot photons?
No, because we want to do experiment with single photons. And if we have dim laser light, and of course we can put dim laser light to this interferometer, but we never know when the photons are arriving and when to look at on the screen, because there are always all kind of other, typically there are some background light and that kind of things. So with this, when we generate these these photon pairs, we can use the other photons to trick our experiment. That means that when the other detector says click, then we know that the other photon from this pair is going, let's say, to the interferometers, and then we can, how can I say, like open a shutter on the screen and look at it where is the second photon there. So it's always like the coincidence type of measurement, because we have all kind of background light always there. So we can remove the background light using this kind of thing, that we just open the shutter. Actually, there are no shutter, but it's doing in electrical way. But anyway, we look at the screen only at a certain moment of time. The time window is typically very, very narrow. It's some couple of nanoseconds, because the photons are created almost at the same time. Actually, they are not created at the same time, because there are quantum feature behind those generation processes. But anyway, they are created almost at the same time, and therefore we can open a shutter for very, very short time window, couple of nanoseconds, and look at it very easy. So that's a technical way to do it. Yeah.
So you get more information than by looking at it precisely.
Yeah, because if it's open all the time, so then I get all kind of background photons, and actually the detector itself can produce light or false alarms, and that. But that's the most important to remove the background.
Okay, thank you.
Yeah.
More questions? Okay, I do have my usual, almost usual question, that is, how did you end up doing this job?
This job?
Quantum optics.
Just by accident. Yeah, really, because I have worked. Not?
I don't know.
Nobody's.
Wasn't me.
Uh-huh. Yes, I said just by accident, because I have worked more than 30 years at the university, and I have changed my research topic at least 4 different times. I have not planned it, that I have changed so many times, and sometimes I do simultaneously let's say 2 or 3 different topics at the same time. I have not planned it, but typically somebody's asked me that can you look at that, and I said yes, of course I can do that, or something else, and because I have changed my research topic so many times, I cannot be expert on any field, but I know, like I say, quite a lot of many things. Many things. Actually, I'm how can I say, yleislääketiede. I'm saying in physics that you can ask whatever. So actually, if you have any question about physics, you can ask me. That's my job in a department that I can get all kind of different questions. Yeah, I think it's best accept. Originally, I'm a theoretician and I study solitons. There are certain nonlinear solution of certain nonlinear differential equations. And after that, I started, because I was also interested in chaos, and then I heard from medicine that they have something peculiar time series signals and asked, can I help? And I did that work some 25 years. I studied the blood pressure regulation of human body. And then I was as a laboratory engineer in laboratories of spectroscopy, and I do all kind of things. And when the professor of this laboratory of spectroscopy retired, the focus of the lab was changed totally, and that was quantum optics. And now I'm there. So I have changed my research topics several times. It always takes, I can say that, 3 years to learn the state of art, whatever it is. And after 3 years, then you can perhaps have your own contribution to new science. But as I said, I have not planned it, but because my career is like this, I have no chances to be a professor, because then you must be narrow. But I must say that I'm extremely happy because it has been very, very, very nice to do all kind of things. And I say that I love optics. I love the components. If I have an infinite number of money, I can buy everything to my lab and just to keep it in fingers and do all kinds of experiments. It's extremely happy to do experiment with light. Of course, it has some challenges because the photons are very fast. But nowadays it's also meet the routine that, because I know that the photons 1 meter they use 3 nanoseconds. 3 nanoseconds is a long time in my lab. And when I put the photons to the optical fiber, I know that they spend 5 nanoseconds in 1 meter of optical fiber. And in all these experiments, when I use these photon pairs, I must always compensate these delays in optical fibers because they are several nanoseconds. And so the speed of light is like a routine to me that I must count it. But it's not so difficult. It would be nice to have a little bit slower photons, and of course it's because it's question about extremely dim light. All the experiments are performed in darkness. So I sit in dark laboratory. Yes, that's of course when you build them you are a lot of light, but when you really do the experiments you are in the dark. Of course there are some light from the computer screen, but anyway it's a dark. Most important tool in my lab is piece of white paper. That's the most important, because that guy can see where the laser beam is. I can put it in different places because I must align the system. Normally the optical setup must be like aligned and trimmed using some laser beam, and later you put single photon beams there because you cannot see it. And a piece of white paper is the most important tool there. Yeah.
Okay, so let's see if there is one more question. Yes?
You showed this beams, 2 identical photons hitting a beam splitter.
Yep.
And they always went the same way.
Yep.
Is it easy enough to explain what quantum mechanical principle makes them do that?
No, basically the photons, because particles are divided in 2 categories, fermions and bosons. Maybe it's just one level of explanation. All particles are divided in fermions and photons. Fermions are bosons, and photons, they are bosons. And this is just again a thumb rule in physics that bosons has a tendency to be together. Actually, yeah. In other words, fermions don't want to be together, and bosons can be together. Yeah. Fermions want to be somehow in different state or different places or whatever. Bosons can be in the same state, in the same moment, in the same position. And that's a one explanation. But of course, it's not a total explanation. But when we model this beam splitter with 2 photons, it's basically a couple of lines of quantum mechanical derivations that you can show that only these 2 possibilities are possible outcomes. Yeah. But it is a little bit, I agree that it's a little bit difficult to understand why, because somehow it's against a classical view or arguments. Yeah. But that's a problem everywhere in quantum physics, to have an intuition, it's difficult. Of course, we must try to also understand. We have a perfect theory. The theory now it has worked about 100 years, never mistakes, never. It works, and the mathematical, how can I say, apparatus is nicely constructed. There are very, very few loopholes anymore in quantum theory, and it can predict all these outcomes of these experiments. But of course, we want to somehow also understand what is going there, and then we need the metaphors and analogs and so on. But that's pity, but we cannot select nature. Actually.
It's a very common feature of quantum physics. We have the math right, but we very often lack intuition or, sort of ways to explain it, other than metaphors that, as you say, they're just metaphors.
Yeah. But most important that you have a theory and maybe some prediction for experiments, and then you have some result and you verify it. Okay, then you have some interpretation, but never the interpretation cannot go to the theory. So that's the most important, because then you get messy out. And the web is full of these kind of misunderstandings and messy outcomes. And when the interpretations are put as a part of the theory, you should never do that in quantum physics.
Okay, maybe if there is one last question, we will take it. And if not before finishing, I would like to advertise our next Science Cafe that will be in 2 weeks on Saturday, December 8th. And this is a little bit of a different Science Cafe because it is about physics, but it is also about a movie that is Interstellar. So I don't know how many of you, can you raise your hand if you have seen Interstellar? Okay, many people have, some have not. And it is, as a physicist, is really something that polarizes very much people, but it is a very, very special movie, unique movie, and we have here our speaker of the Interstellar talk. Before, I will ask him to say briefly a few words about the next Science Cafe, but before I have to say the reason why this is different Science Cafe. That's because we are going actually to see first the movie. For those of you who haven't seen it, or for those of you who want to see it, this will be at Kino Diana, that is here close by. You will find all the information in the Facebook or our webpage. And after having seen the movie, there will be the Science Cafe talk by Guy, who is our new postdoc in the Laboratory of Theoretical Physics in the Turku Quantum Technology Group. So maybe you want to say a few words about that. What is it about?
So hi everyone. So the reason why we speak about Interstellar is because the scientific advisor of the movie was Kipling, who was awarded the Nobel Prize in Physics recently, and he calculated everything for the movie. So he actually did, and he passed all the calculations to the science fiction people in the production unit. And so the visual representations of the movie are extremely accurate. And also, there is a very interesting point, which is, so it's a very good movie to start talking about physics, like general relativity, black holes, wormholes, and so on. But also, it has this, so most of you have seen it, and you know that the ending is very puzzling. No, I'm not saying the ending, of course not. It's puzzling. It's a puzzling ending that no one really gets, and it's fascinating to see that there's actually a lot of thought behind that ending, and we will explain it. So I hope to see you all there.
Okay, yes, so December 8th. Remember, because we have to see the movie, this will start early. So it will start, it's on Saturday, December 8th, and it starts at 2 at Kino Diana. And after that, there will be the Science Cafe talk. So if you have seen the movie, or if you can't come and you want to see the movie otherwise, then just come to the Science Cafe. That will start, okay, the movie lasts 3 hours, so we will start it at 5:30, the Interstellar talk. The talk will start at 5:30. The movie will begin at 2 because it's a long movie. But what I can say is that I'm sure that you will. I don't know. I mean, you will understand so much of the. He wrote a book also. Actually, it's based on a book. The science, not him, but Kip Thorne wrote the Science of Interstellar is called. And so it really many things that sounded, just weird. They sort of start to make sense. It's really very interesting. And after this, I would like to thank you so much again, Tom, for his very interesting talk, and please stay here and have a beer and chat with Tom a little bit more if you want to. Thank you. Thanks.